Galaxies are vanishing from our view across the cosmos. The phenomenon of disappearing galaxies and their lost light is forcing astronomers to rewrite their understanding of the universe itself. By the end of this exploration, you will grasp the hidden forces actively erasing cosmic light and what this means for everything we see in the night sky. What cosmic architecture is powerful enough to make entire galaxies fade away, and what secrets are hidden in the darkness they leave behind? How much of the true universe remains invisible to our eyes? The universe holds onto its secrets with a tenacity that defies our gaze. We have long believed galaxies to be the permanent landmarks of the cosmos, but the observational record tells a different, more unsettling story. Entire galactic systems are vanishing from our sight, their collective starlight fading into an imperceptible whisper. This is the phenomenon of lost light, where a galaxy that once shone brightly in a telescope's eyepiece simply cannot be found again. Historical astronomy is dotted with such ghost stories. In the early 20th century, astronomers like Edwin Hubble and others catalogued faint, nebulous objects, some of which were later sought in vain. These were not simple mistakes, but documented presences that later surveys failed to redetect, sparking debates that linger to this day. Was the original observation an error, or did something fundamental change in that distant patch of sky? This cosmic vanishing act forces us to confront a profound question about our own home. The Milky Way, a brilliant spiral of billions of stars, may not always grace the universe with its light. Billions of years from now, could our galaxy too fade from the view of some distant observer, becoming just another entry in a catalogue of cosmic ghosts? The gradual, inexorable dimming of galactic light is not a sudden extinction, but a slow fade into obscurity, and it remains one of the most compelling puzzles in modern astronomy. The true architecture of the cosmos is built from a substance we cannot see, dark matter, an invisible form of matter that outweighs all the stars and galaxies combined, weaves a gravitational web across the universe. This hidden scaffold dictates the motion and fate of everything we observe, and its immense gravitational pull might be the very force that tears galaxies apart. Think of a galaxy not as an isolated island, but as a ship caught in an invisible, relentless current. The dark matter halo surrounding a galaxy is not a gentle cradle, it is a dynamic and sometimes destructive environment. Over billions of years, the relentless tug from these massive, unseen structures can stretch a galaxy to its breaking point. Astronomers have witnessed this cosmic tug-of-war in action. They observe galaxies at the edges of massive clusters, their shapes grotesquely distorted into long, thin streams of stars. These are not random patterns, they are the unmistakable fingerprints of dark matter's gravitational grip, pulling stars away from their galactic homes one by one. Leading cosmologists suggest that dark matter halos act like cosmic thieves, gradually siphoning stars from a galaxy's outer regions. This process, known as tidal stripping, is a slow and silent disintegration. The galaxy does not explode, it simply unravels, its stellar population scattered into the darkness between galaxies. The light from those stolen stars does not vanish instantly, but it becomes so faint and diffuse that it slips below the detection threshold of our most powerful telescopes. What was once a brilliant pinwheel of billions of stars fades into the background, becoming an imperceptible smudge and then nothing at all. This invisible cosmic architecture, responsible for holding the universe together, may also be the very reason so much galactic light is lost from our view. Even as dark matter pulls galaxies apart, another force is working on a far grander scale to hide the cosmos from view. The very fabric of space itself is stretching, and this expansion is systematically stealing light from our eyes. When astronomers say the universe is expanding, they do not mean galaxies are simply flying apart through a static void. Instead, the space between galaxies is growing, like dots on an inflating balloon being pushed further and further apart. This relentless stretching does something profound to the light traveling across these vast distances. It physically elongates the light waves, systematically shifting them toward the red end of the spectrum. This is the phenomenon of cosmological redshift. Imagine a fire engine's siren. As it moves away from you, the sound waves stretch out and the pitch drops to a deeper tone. Light behaves in a similar way. A galaxy racing away from us because of the universe's expansion has its light stretched during its multi-billion-year journey to Earth. The blue and white light from its hottest, youngest stars is stretched, becoming redder and redder. The further away a galaxy is, the faster it recedes, and the more extreme this redshift becomes. Eventually, for the most distant galaxies, the stretching is so severe that their visible light is shifted completely out of the visible spectrum and into the infrared, a form of light our eyes cannot see. This is not a dimming of the bulb, but a fundamental change in the nature of the light itself. The galaxy is still shining just as brightly, but its light has been transformed into something invisible to our telescopes, effectively causing it to vanish from certain observational surveys. This process creates a fundamental horizon for our vision, a cosmic veil dictated by the expansion of space. Unlike the violent disruption caused by dark matter, this disappearance is a quiet, inevitable fading, a direct consequence of the universe's own accelerating growth. The most distant and ancient galaxies are being systematically erased from our view, their light stretched into oblivion by the expanding cosmos. How many more galaxies lie just beyond this redshift horizon, their stories forever lost to the stretching void? But the universe has more than one way to hide its treasures. Beyond the grand forces of gravity and expansion, a far more tangible veil hangs in the depths of space. Vast clouds of fine, sooty particles drift in the emptiness between galaxies, forming an immense cosmic fog. This intergalactic dust, composed of tiny grains of carbon and silicon, acts as an almost perfect light-blocking agent. When starlight from a distant galaxy journeys for millions of years to reach us, it must pass through this pervasive haze. The dust does not simply dim the light, it absorbs and scatters it, redirecting the photons into random trajectories. It is like trying to see the beam of a distant lighthouse through a thick, swirling sea fog. The light is there, but it is hopelessly diffused and lost before it can ever reach your eyes. Astronomers have mapped specific regions of space where this effect is extreme. In certain directions, we find immense galaxy clusters that appear to be surrounded by voids, areas curiously empty of any background galaxies. For a long time, these zones were considered genuine gaps in the cosmic structure, but with telescopes capable of observing in infrared and other wavelengths, a different truth emerged. These are not voids at all. They are simply the universe's dark zones, where thick curtains of intergalactic dust have completely obscured the brilliant cities of stars lying behind them. Recent surveys have revealed intricate patterns in this dust distribution, showing that it is not a uniform screen but a patchy, filamentary web. This means our map of the universe is fundamentally skewed, pockmarked with blind spots where galactic light is silently being absorbed. The sheer scale of this obscuration is staggering, with some estimates suggesting a significant percentage of all galactic light is permanently filtered out by this cosmic grime. So when we peer into a seemingly empty patch of sky, we are not looking at nothingness, we are staring directly into a cosmic fog bank, its dense haze ensuring that the brilliant lights beyond remain a secret forever kept. There is another, more violent path to disappearance unfolding all around us. Galaxies are not solitary giants, they are social creatures bound by gravity, and their close encounters often end in a form of cosmic cannibalism. When two galaxies drift too close, their mutual gravitational attraction pulls them into a fatal dance. This is not a gentle merging, but a chaotic, billion-year-long process that fundamentally erases the identities of the galaxies involved. The smaller galaxy is torn apart, its stars scattered and its structure dissolved into the larger system. Its distinct light signature, the very thing that made it a unique island in the void, is extinguished forever. We can see this process at various stages across the cosmos. Look at the famous antennae galaxies, two spiral galaxies locked in a violent embrace. Long, streaming tails of stars, flung out by immense gravitational tides, arc away from the central collision. These tidal tails are the shredded remains of what were once orderly spiral arms. Within a few 100 million years, the two distinct cores will coalesce into a single, new entity, likely an elliptical galaxy. The original spiral galaxies will have vanished completely, their light replaced by the different, more diffuse glow of the new hybrid. This transformation is not just about rearranging stars, it is about erasing history. The merger triggers ferocious bursts of star formation as clouds of gas collide and compress, blazing with intense blue light before quickly burning out. The resulting galactic remnant often settles into a smooth, featureless shape, its distinctive spiral arms or irregular structure lost to the chaos of the collision. So when we look at a quiet elliptical galaxy, we may be staring at the grave of two or more spiral galaxies that once shone brightly, their individual lights consumed in a fiery merger. The universe is constantly rewriting its own map, erasing old landmarks to create new ones, and in the process causing countless galaxies to effectively disappear from our catalogues. A galaxy can die from the inside out. While collisions and dark matter tear them apart externally, a quieter, more insidious fate awaits many galaxies as their internal fires simply go out. This process is known as quenching, and it systematically transforms brilliant, star-forming spirals into dim, red, and dead relics. A quenched galaxy has not exploded or vanished in a flash. It has entered a state of cosmic retirement, its light slowly fading over billions of years as its stellar population ages with no new stars to replenish the glow. The vibrant blue light of hot, young, massive stars is the first to disappear, leaving behind the cooler, redder glow of longer-lived, older stars. Over eons, even these stars will burn out one by one, their light winking out forever, leaving the galaxy progressively dimmer. The question is, what starves a galaxy of its ability to create new suns? The primary culprit is often a simple lack of fuel. Galaxies form new stars from vast reservoirs of cold gas, primarily hydrogen. This interstellar fuel can be depleted in several ways. A galaxy might simply use it all up in a final, glorious burst of star formation, burning through its reserves so quickly that nothing is left for future generations. Alternatively, as a galaxy moves through the hot plasma that fills galaxy clusters, this intergalactic medium can act like a powerful wind, physically stripping the cold gas away in a process called ram pressure stripping. The galaxy is left gasping for fuel, its star-forming machinery grinding to a halt. But perhaps the most dramatic quenching mechanism comes from the very heart of the galaxy itself. At the center of nearly every large galaxy, including our own Milky Way, lurks a supermassive black hole. When this black hole actively feeds on surrounding matter, it does not do so quietly. The infalling material heats up to incredible temperatures, blazing with light and unleashing powerful jets of energy that erupt from the galactic core. This is known as active galactic nucleus feedback. Think of it as a cosmic thermostat. The tremendous energy blasting out from the black hole heats the surrounding gas, preventing it from cooling down and collapsing to form new stars. In the most extreme cases, these jets can blow the entire gas reservoir clean out of the galaxy, shutting down star formation for good. Astronomers see evidence of this in galaxies where brilliant quasars, the most luminous type of active black hole, appear to have blown away their own galactic fuel supply, leaving behind a quenched and fading galaxy. The timelines for quenching vary dramatically. Some galaxies experience a rapid shutdown, their star formation cut off in a relatively short cosmic timespan. Others undergo a slow, protracted strangulation, a gradual decline in new star birth over billions of years. Recent research suggests that a galaxy's environment plays a crucial role, with dense galaxy clusters being efficient quenching grounds, while isolated galaxies can sometimes retain their star-forming gas for much longer. Each quenched galaxy, whether it faded quickly or slowly, represents a permanent loss of future light from the universe. Its current stars will continue to dim, and with no new stars being born, that region of the cosmos will grow progressively darker. This silent, internal fading is one of the most significant contributors to the universe's disappearing light, a slow burn-out that is happening all around us. Deep within the heart of nearly every galaxy, a monster lies in wait. These supermassive black holes are not merely passive holes in space-time. They are dynamic engines capable of both brilliant creation and absolute destruction. Their influence extends far beyond their event horizons, shaping the entire galaxy that hosts them through a powerful process known as feedback. This cosmic tug of war between creation and destruction is one of the most critical forces determining whether a galaxy shines brightly or fades into darkness. When a black hole actively feeds, the infalling material doesn't just vanish. It forms a superheated, swirling disk of gas and dust. This accretion disk glows with the intensity of billions of stars, becoming what we call an active galactic nucleus, or a quasar. For a time, this makes the galaxy's core one of the most luminous objects in the entire universe. But this brilliance comes at a terrible cost. The immense energy and radiation pouring from the black hole, along with powerful jets of particles traveling at nearly the speed of light, blast outward into the galaxy. Think of it as a cosmic hurricane roaring through the galactic system. These outflows of energy act like a powerful thermostat, regulating the galaxy's ability to form new stars. The vast clouds of cold gas, the raw material for future suns, are violently heated by this feedback. Instead of cooling down and collapsing under their own gravity to ignite new stars, the gas is kept hot and diffuse, unable to coalesce. In more extreme cases, the black hole's fury doesn't just heat the gas, it physically ejects it. These galactic winds can blow the entire reservoir of star-forming fuel clear out of the galaxy, stripping it bare. We have observed this dramatic process in action. Astronomers study galaxies where quasars are actively expelling colossal amounts of gas, sometimes the equivalent of hundreds of solar masses each year. The galaxy is essentially blowing out its own candle, sacrificing its long-term future for a short, spectacular blaze of glory. One of the most compelling pieces of evidence linking black holes to galactic dimming is found in massive, dead galaxies. These ancient systems, known as red and dead ellipticals, are filled with old, red stars and possess almost no young, blue stars. At their centers, we often find supermassive black holes of staggering size, far larger than the one in our own Milky Way. The correlation is too strong to ignore. The most massive black holes are consistently found in galaxies that have stopped forming stars. It appears that in the distant past, these black holes went through a ferocious feeding phase, and their resulting feedback was so powerful that it permanently quenched their host galaxies. The black hole, after expelling or heating all the available fuel, eventually goes quiet itself, leaving behind a dimming galactic relic. This feedback cycle solves a long-standing puzzle for astronomers. Without a regulating mechanism like this, the most massive galaxies would have continued forming stars at a frantic pace, growing to unrealistic sizes. The black hole acts as a built-in governor, a self-destructive mechanism that ultimately limits the galaxy's growth and seals its fate. The light from new stars is never born, and the galaxy's overall brightness begins a slow, inexorable decline. So the very same cosmic engine that can produce the most intense light in the universe is also one of the primary architects of its eventual disappearance. The relentless pull of gravity does more than just guide galactic orbits. It can systematically dismantle a galaxy piece by piece. This cosmic dissection is known as tidal disruption, a process where a galaxy is slowly torn apart by the immense gravitational forces within a dense cluster. Imagine a galaxy not as a solid object, but as a vast collection of individual stars, each one held in a delicate balance between the galaxy's own gravity and the external pull of its neighbors. In the crowded core of a galaxy cluster, that balance is shattered. The galaxy experiences a gravitational tug of war, stretched from all sides by the combined mass of hundreds or even thousands of other galaxies and their immense dark matter halos. This differential force, the tidal force, is strongest on the galaxy's outer regions, where the gravitational bond to the galactic center is weakest. It is here that the stripping begins, with stars being gently but persistently plucked from their orbits and flung into the intergalactic void. We can see the evidence of this stellar theft in stunning detail. Look at the Coma cluster, a dense swarm of galaxies millions of light-years away. Between the brilliant galaxies themselves, astronomers have detected faint, ghostly rivers of light, streams of stars that no longer belong to any single galaxy. These are the orphan stars, the casualties of this quiet gravitational war, their collective glow forming an ethereal intracluster light that permeates the entire cluster. For any single galaxy caught in this environment, the consequence is a gradual but irreversible dimming. The process starts at the edges, stripping away the faint, diffuse halo of old stars that surrounds a galaxy's main disk. But over billions of years, the stripping can reach deeper, pulling away entire spiral arms or disrupting the delicate structure that makes a galaxy recognizable. The galaxy loses not just its stars but its very identity. Its total luminosity drops as its stellar population is scattered. A galaxy that was once a brilliant beacon can, over cosmic timescales, be reduced to a faint, diffuse smudge. Its light signature becomes so weak that it slips below the detection limit of our surveys. What was once catalogued as a distinct galaxy might later be recorded as mere background noise, or simply vanish from subsequent observations entirely. This tidal stripping is a primary reason why the cores of ancient galaxy clusters are often dominated by featureless elliptical galaxies, the survivors of this relentless gravitational grinding. Their spiral neighbors have been stripped, faded, and effectively erased from our view, their light lost to the dark currents between the galaxies. Long before galaxies assembled into the grand structures we see today, the entire universe was plunged into a fog of its own making. This era, known as the Epoch of Reionization, was a universal transformation that fundamentally reshaped how light could travel through space. For hundreds of millions of years after the Big Bang, the cosmos was filled with a thick soup of neutral hydrogen gas. This gas acted like a pervasive cosmic haze, absorbing the high-energy ultraviolet light from the first stars and galaxies. Imagine a young galaxy blazing with the light of its first brilliant stars, only to have that light almost immediately swallowed by the surrounding murk. Its story would be trapped, its light unable to journey across the cosmos to our telescopes. This was the reality of the universe's infancy. The neutral hydrogen atoms were so efficient at capturing specific wavelengths of light that they created an effective horizon, a wall in time beyond which we cannot directly see. The light from those earliest galactic structures was not lost in transit. It was stopped at the source, absorbed and scattered into a diffuse glow that we can no longer decipher. Then a profound shift began to occur. The intense radiation from the first generations of stars and from voracious black holes started to tear electrons away from the hydrogen atoms, ionizing them in a process that swept across the universe. This was reionization, the moment the cosmic fog began to lift. But this lifting was not a gentle clearing. It was a turbulent and patchy process, creating bubbles of transparent, ionized gas that slowly grew and merged. For the galaxies shining inside regions still filled with neutral hydrogen, the effect was a temporary disappearance. Their light remained imprisoned until the ionization front finally reached them. Recent observations from the most powerful space telescopes are now piecing together this ancient timeline. They suggest that reionization was a drawn-out affair, completing only when the universe was around 1 billion years old. The consequence of this universal sea change is that a vast portion of the light from the very first galaxies was permanently filtered out. We see their descendants, the galaxies that shone just after the fog cleared, but the true pioneers, the very first cities of stars, are effectively hidden from our direct view. Their light was absorbed and transformed by the primordial fog of a universe still in its formative years, causing a disappearance so complete that we can only infer their existence from the shadows they cast on the cosmos itself. Our cosmic census of galaxies is far from perfect, filtered through the imperfect lens of our own technology. There are countless instances where a galaxy has not vanished from the universe, but has simply slipped below the detection threshold of our telescopes. This is the illusion of disappearance, a phantom absence created by the very tools we use to search the skies. Every survey, every deep field image, carries with it a set of observational biases, a set of rules for what it can and cannot see. A telescope designed to capture the specific light of hot, young stars will naturally miss galaxies dominated by older, redder suns. An instrument sensitive only to a narrow band of the electromagnetic spectrum is effectively blind to entire classes of celestial objects. The history of astronomy is filled with these artificial vanishings. An object catalogued in a photographic plate survey from the early 20th century might appear as nothing more than a faint smudge, a blur that later, more sensitive digital searches failed to confirm. For decades, astronomers debated whether these were real objects that had changed or simple flaws in the emulsion. In many cases, the answer came with technological advancement. The launch of space telescopes capable of observing in infrared light revolutionized our view. Vast swaths of the sky that once seemed empty suddenly teemed with previously invisible galaxies, their light redshifted into infrared wavelengths by the universe's expansion. These were not new galaxies, they had been there all along, hidden in plain sight, their existence masked by the limitations of our own eyes and instruments. What we perceive as a stable map of the cosmos is in fact a snapshot, a single frame in a moving picture, limited by the resolution and sensitivity of our current technology. Every time we build a better telescope, we pull back another layer of the cosmic veil, revealing lights we never knew were there and correcting the record on those we thought were lost. Perhaps the most elusive phantom of the cosmos is a galaxy that was never meant to shine at all. We have explored how light is stripped, stretched, and hidden, but what if some galactic structures were born dark? This is the mystery of dark galaxies, vast islands of dark matter that failed to assemble a significant population of stars, leaving them as cosmic phantoms, massive yet nearly invisible. The theoretical framework for these entities is compelling. We know dark matter clumps together under gravity, forming the scaffolding for all cosmic structure. But in some early pockets of the universe, conditions may have been just wrong for star formation to ignite. Perhaps the primordial gas within these dark halos was too hot to collapse, or maybe it was stripped away by external forces before the first stars could even form. The result would be a galaxy in every sense but one, a colossal gravitational anchor made almost entirely of unseen matter, its visible light output a faint, negligible whisper. So how do you find a galaxy that refuses to be seen? Astronomers turn to the subtle art of gravitational lensing. When light from a distant, bright object passes through a massive foreground structure, its path is bent like a lens made of pure gravity. If a dark galaxy lies along that line of sight, its invisible mass will warp the background light in a distinct, telltale way. It creates a ghostly fingerprint in the distortion of a distant galaxy's image, a signature of mass without light. Another method involves searching for isolated clouds of hydrogen gas that are rotating at high speeds, suggesting they are held together by a powerful gravitational field, yet they emit no starlight to account for that mass. For years, these were just theoretical curiosities, but recent observations have produced compelling candidates. One of the most famous is an object known as Dragonfly 44. This ultra-diffuse galaxy in the Coma cluster has the mass of our own Milky Way, but its light output is thousands of times fainter, meaning over 99% of its mass must be dark matter. While Dragonfly still has some stars, it points the way to even darker objects. Another tantalizing clue comes from studies of the faint, distorted images of background galaxies, where astronomers have mapped invisible mass concentrations that have no stellar counterpart at all. These are the prime suspects, the potential dark galaxies hiding in plain sight. Their existence would solve persistent riddles in our maps of the cosmos, explaining unexpected gravitational pulls and the peculiar motions of some visible galaxies that seem tugged by unseen neighbors. If this population of dark galaxies is real and abundant, it means our census of the universe is not just incomplete, it is fundamentally skewed. We have been counting the streetlights while missing the entire city. The light of a vanished galaxy does not always disappear without a trace. Like a sound echoing long after the source has gone silent, the photons emitted by stars billions of years ago can continue their journey through the cosmos, carrying the ghostly imprint of their origin. This is the field of cosmic archaeology, where astronomers act as detectives, sifting through lingering radiation to reconstruct the histories of galactic systems that no longer exist. They are not looking for the galaxies themselves, but for the faint, persistent echoes they left behind. One of the most powerful tools in this search is gravitational lensing, a natural phenomenon where the gravity of a massive foreground object, like a galaxy cluster, bends and magnifies the light from objects far behind it. This cosmic lens can do more than just magnify. It can also create multiple images and dramatic arcs of light. When astronomers observe a strange, warped arc of light in a cluster, they are often looking at the distorted image of a background galaxy. But sometimes the source of that light is gone, having merged or faded in the billions of years it took for its light to finally reach us. The arc we see is a ghost, a fossilized image of a galaxy from a much younger universe. By analyzing the properties of this light, its color, its intensity, and its structure, scientists can perform a kind of astronomical autopsy, determining what type of galaxy it was, how many stars it held, and even the manner of its disappearance. Another form of cosmic echo comes from the diffuse glow that permeates galaxy clusters. This intracluster light is made of billions of orphan stars, ripped from their home galaxies during violent encounters and tidal stripping. The collective glow of these stars is a direct fossil record of the dismantling process, a permanent archive of all the galactic light that was scattered and lost. By mapping the distribution and chemistry of this faint light, astronomers can piece together the assembly history of the entire cluster, revealing how many galaxies were consumed to build the giants we see today. There are even more subtle echoes to be found in the background radiation of the universe. The total extragalactic background light is a sea of photons that includes the combined light of every star and galaxy that has ever shone, stretched and diluted across time and space. While it appears as a uniform glow, sophisticated analysis can, in theory, tease out the contributions from different cosmic eras, including the light from entire generations of galaxies that have since faded away or merged beyond recognition. Each of these forensic techniques allows us to see beyond a simple snapshot of the cosmos. They let us read the universe like a layered history book, where the stories of long-dead galaxies are written in the faint, lingering light that still washes over us. By studying these cosmic ghosts, we do more than just catalog the missing. We begin to understand the complete life cycle of galaxies, from their fiery birth to their quiet or violent end, and the myriad ways the universe conspires to hide its oldest lights from our view. One of the most humbling moments in astronomy came not from finding something, but from looking at nothing. Astronomers pointed the Hubble Space Telescope at a patch of sky so blank it was considered a celestial void, a place devoid of any known stars or galaxies. For 10 consecutive days, the telescope gathered every possible photon, and the resulting image, the Hubble Deep Field, fundamentally rewrote our cosmic map. That tiny, empty spot, no bigger than a grain of sand held at arm's length, was filled with a breathtaking spectacle, not of dozens but of thousands of galaxies. Each smudge of light was an entire island universe, some as they appeared when the cosmos was in its youth. This single observation revealed the staggering density of the universe, proving that what we perceived as empty space was actually a vibrant, crowded metropolis of galactic systems. The deep field was a powerful lesson in observational bias, showing that our previous surveys had simply been too shallow, their exposure times too short to capture this faint, distant population. It forced astronomers to confront a simple truth: the sky only looks empty because we are not looking deeply enough. This revelation directly addressed the mystery of lost light. Many of the galaxies that seemed to vanish from older catalogs were not gone. They were merely hovering at the very edge of detectability. The deep field proved that countless galaxies exist in a state of perpetual faintness, their light so dim and diffuse that they slip in and out of view depending on the power and persistence of our gaze. The image also revealed why some regions of space appear barren. It is not that galaxies are absent, but that their distribution is like a forest viewed from a distance. Some lines of sight are blocked by closer trees, while others open up to reveal vast depths filled with countless more. In the cosmic forest, thick curtains of dust or the simple sheer distance can make a densely packed region appear as a void. This profound shift in perspective reshaped the entire hunt for missing galactic light. It taught us that to find what is lost, we must stare longer and deeper into the darkness, pushing our instruments to see the universe not as it appears in a quick glance, but in the patient, accumulated glow of its truest form. The Hubble Deep Field did not just fill an empty spot in the sky, it filled a void in our understanding, proving that the universe's greatest secrets are often hidden in plain sight, waiting only for us to look closely enough. The universe hides its brightest secrets in plain sight, just beyond the narrow visual spectrum our eyes can perceive. For generations, astronomers mapping the cosmos with optical telescopes saw only a fraction of the true picture, their surveys systematically missing entire populations of galaxies whose light had been transformed. This is where infrared astronomy steps in, pulling back a cosmic curtain to reveal a hidden universe teeming with light we once thought was lost. The James Webb Space Telescope, with its powerful infrared eyes, is not just finding new objects, it is correcting our entire galactic census, showing us that what we called emptiness was actually a realm of brilliant, obscured activity. The reason for this discrepancy lies in the fundamental nature of light and cosmic distance. As the universe expands, it stretches the light from the most distant galaxies, shifting it from the visible blue and ultraviolet colors in which it was emitted all the way into the infrared part of the spectrum. A galaxy that would have appeared blue and vibrant to a nearby observer billions of years ago has, by the time its light reaches us, been redshifted into an invisible infrared signature. To traditional optical telescopes like Hubble, these galaxies are simply absent, vanished from view. But to an instrument like James Webb, they blaze with intense clarity. We have seen this play out in stunning new deep field images. Regions of space that Hubble revealed as dark voids are, in James Webb's infrared view, packed with a dizzying array of spiral disks and glowing clumps, entire cities of stars that were there all along, their light simply translated into a language Hubble could not read. Another profound revelation concerns dust-obscured star formation. The most fertile stellar nurseries are often enshrouded in thick cocoons of cosmic dust, which block visible light but glow brightly in the infrared. An optical survey might see only a dim, red, and quiet galaxy, but an infrared telescope peers straight through the dust, revealing a ferocious heart of newborn stars blazing within. These dust-hidden galaxies are some of the most productive star factories in the universe, and yet they contributed almost nothing to our traditional maps of cosmic light. Their incredible luminosity was being absorbed by dust and re-radiated in the infrared, a wavelength invisible to our previous tools. This dual discovery of redshifted and dust-shrouded galaxies forces a dramatic reassessment. A significant portion of the universe's stellar birth and galactic structure was not missing at all. It was merely waiting in the dark for us to learn how to see. Our cosmic map resembles a vast, tangled web more than a random scattering of isolated islands. This cosmic web, a sprawling architecture of dark matter filaments, forms the true backbone of the universe, with galaxies strung along its luminous threads like pearls on an invisible string. Where these filaments intersect, we find the immense, crowded metropolises of galaxy clusters, but between the threads stretch the cosmic voids, unimaginably vast deserts of near emptiness that can span hundreds of millions of light years. A galaxy's position within this grand structure, whether nestled in a dense knot or isolated in a silent void, profoundly influences not only its fate but its very visibility to us. The most brilliant galactic cities, those at the crowded cluster centers, often hide their own neighbors. Their intense collective light can create a glare that washes out the fainter glow of smaller, background galaxies, a phenomenon known as crowding. Trying to pick out a single, distant galaxy in this stellar metropolis is like trying to spot a lone, faint candle standing directly in front of a massive searchlight. The overpowering brightness of the foreground cluster effectively erases the more distant object from our view. Conversely, a galaxy adrift in one of the great voids presents a different challenge. These isolated systems are often starved of the gas needed for vigorous star formation, making them intrinsically dim and difficult to detect across the vast gulf of empty space. Their faint light can easily fall below the detection threshold of our surveys, causing them to be systematically missed in our cosmic census. The geometry of the web itself also creates a fundamental observational bias. When we look along a dense filament, our line of sight passes through a long succession of galaxies, creating a crowded, overlapping chain that is easier to detect. But when we point our telescopes towards the center of a void, we are staring down a nearly empty corridor, a perspective that makes the universe appear far more barren than it truly is. Recent, ambitious mapping projects have used the subtle distortions of gravitational lensing to trace the invisible dark matter filaments of the web. These maps confirm that the densest regions of the web are where a significant amount of ordinary matter, in the form of faint dwarf galaxies and diffuse gas, is predicted to reside. The light from these countless small, faint systems is blended together into a diffuse, unresolved glow that permeates the web, a collective light that is real and present but too spread out for our telescopes to pinpoint its individual sources. This means our inventory of galactic light is not just a list of missing entries, it is skewed by the very architecture of reality. We are inherently better at counting the bright pearls on the string than we are at seeing the dim, countless grains of sand that fill the spaces between them, leaving a substantial portion of the universe's total illumination hidden within the complex, shadowy topology of the cosmic web. A galaxy's disappearance can sometimes be a spectacular, fleeting performance rather than a final exit. Time-domain astronomy, the practice of watching the sky for change, reveals a universe in constant, dramatic flux, where a galaxy's light can be violently rewritten in an instant. These are not the slow fades of tidal stripping or quenching, but sudden, catastrophic outbursts that can mimic a total vanishing. Consider the case of a seemingly ordinary galaxy that, over a matter of weeks, becomes hundreds of times brighter than its entire stellar population. This is the signature of a tidal disruption event, where a star wanders too close to the galaxy's central supermassive black hole. The black hole's immense gravity shreds the star, stretching it into a brilliant stream of incandescent gas before consuming it. For a short time, the light from this single event can outshine every star in the galaxy combined, creating a temporary beacon that then fades back into obscurity over months or years. To an astronomer taking a single snapshot in time, this galaxy would appear to have undergone a mysterious, brilliant flare before dimming to near invisibility. Another transient phenomenon comes from the most powerful explosions since the Big Bang itself, gamma-ray bursts. When a massive star collapses or two ultra-dense neutron stars merge, they can unleash a focused beam of energy so intense that it briefly outshines the rest of the gamma-ray universe. If such a beam were pointed directly at Earth from within a distant galaxy, it would create a fleeting, overwhelming point of light that could blind our instruments to the galaxy's underlying steady glow. Once the burst fades after only a few seconds or minutes, the host galaxy might seem to have vanished, its permanent light drowned out by the memory of that temporary, apocalyptic flash. To catch these cosmic will-o'-the-wisps, astronomers have launched dedicated monitoring programs that scan the same patches of sky night after night. Projects like the Zwicky Transient Facility and the upcoming Vera C. Rubin Observatory are designed to detect these subtle changes, building a movie of the cosmos instead of a photo album. They are already discovering new classes of variable phenomena, such as repeating partial disruption events or mysterious, slow-evolving supernova that could easily be mistaken for a galaxy flickering out of existence. Each new transient event catalogued is a potential clue, a piece of a puzzle that explains why our static maps of the universe are so often deceived by its dynamic, explosive reality. A galaxy can be caught in the crossfire of its own creation. These immense stellar nurseries where thousands of new stars ignite in a frenzy of birth generate more than just light. They unleash hurricane-force winds that can ultimately doom their galactic home. The most massive of these newborn stars burn hot and fast, living short, violent lives that end in supernova explosions. Each detonation sends a cataclysmic shockwave blasting through the surrounding gas, and collectively, these endless stellar tempests drive a powerful galactic wind. This wind acts like a cosmic pressure washer, scouring the galaxy of the very gas clouds that would have formed the next generation of stars. We have witnessed this self-destructive process in galaxies like Messier 82, a classic starburst galaxy where star formation is occurring at a ferocious rate. Observations reveal colossal fountains of material, glowing with the heat of millions of degrees, being ejected perpendicular to the galaxy's disk. This is not a gentle leak, it is a systematic evacuation of the galaxy's future. The wind carries away immense quantities of hydrogen gas, the primary fuel for new stars, along with heavier elements and dust particles forged in stellar furnaces. Once this material is pushed beyond the galaxy's gravitational grasp, it is lost forever, drifting into the vast intergalactic medium. The galaxy's brilliant blue light, powered by its short-lived, massive stars, begins to flicker and fade as the stellar nursery is literally blown empty. Without a fresh supply of gas to collapse into new suns, the galaxy's overall luminosity enters an irreversible decline. This gradual dimming, driven by the very winds of star birth, transforms a vibrant, blue spiral into a quieter, redder, and progressively darker system over hundreds of millions of years. The galaxy is not being destroyed from the outside, but is instead exhausting its own potential in a final, spectacular, and ultimately self-defining blaze of glory. Even the most powerful telescope in history sees only a sliver of the cosmos. Our deepest surveys, for all their grandeur, capture a minuscule fraction of the total universe, a cosmic grain of sand on an endless beach. This fundamental limitation introduces a subtle but powerful bias known as cosmic variance. It is the simple statistical truth that different patches of space, even if they are the same size, will naturally contain different numbers of galaxies. Some volumes will, by pure chance, be overcrowded, while others will be surprisingly empty. When we point our instruments at one of these emptier regions, we might hastily conclude that galaxies have vanished, when in reality we have just drawn a short straw in the cosmic lottery. Imagine counting the number of cars in a single city block to estimate the total traffic in a continent. Your results would vary wildly depending on whether you picked a quiet suburban street or the heart of a metropolis. This is the challenge astronomers face on a galactic scale. The original Hubble Deep Field itself was a perfect example. Had it been pointed at a slightly different, less dense part of the sky, it would have revealed far fewer galaxies, potentially leading to a very different and more barren understanding of the early universe. These sample limitations can create phantom disappearances. A galaxy catalogued in one survey might fall right on the edge of a second survey's field of view, or its light might be just faint enough to be excluded by that survey's specific detection threshold. It hasn't gone anywhere, but to our imperfect maps it has effectively vanished. To combat this illusion, astronomers turn to sophisticated statistical tools. They run millions of computer simulations of the universe, populating virtual space with galaxies based on our best models of cosmic structure. By comparing these simulated skies to our actual observations, they can calculate the expected range of cosmic variance for any given survey volume. If the number of missing galaxies in a particular region falls within this expected range of statistical noise, the disappearance is likely just an artifact of our limited sample. But if the number is significantly higher than chance allows, it points toward a genuine physical phenomenon at work, like the tidal stripping or quenching we have discussed. This painstaking statistical work is the unglamorous backbone of cosmic detective work, separating true celestial mysteries from the simple, random clumpiness of an immeasurably vast universe. It reminds us that our view is always and will always be a carefully interpreted sample, a single window looking out upon an infinity of shadows and light. Our own cosmic backyard holds a ghost story of its own. The Milky Way should be surrounded by a vast swarm of small satellite galaxies, hundreds of them according to our most trusted models of cosmic structure. Yet when we count them, we find only a few dozen. This is the missing satellite problem, a quiet but persistent anomaly that suggests our neighborhood is far emptier than it ought to be. Where did all those dwarf galaxies go? The answer seems to be that they were never bright enough for us to see in the first place, victims of a process that strangled their light at birth. The leading theory points a finger at the very first stars. In the early universe, these primordial giants burned ferociously and died young in supernova explosions that flooded space with intense ultraviolet radiation. This cosmic fallout had a chilling effect on the smallest dark matter halos, the cradles meant for dwarf galaxies. The radiation heated the sparse gas within these tiny halos, preventing it from cooling, collapsing, and igniting into stars. Without stars, these potential galaxies remained dark, massive clumps of invisible matter adrift in the void, their light stillborn. Other small galaxies might have formed a handful of stars, only to have their faint glow extinguished by the harsh environment of our galactic neighborhood. A dwarf galaxy venturing too close to the Milky Way's immense gravitational field can be torn apart by tidal forces, its meager stellar population scattered into faint, undetectable streams. Or its tenuous gas reservoir could be stripped away by the pressure of the hot plasma that fills the space around our galaxy, a process that shuts down any future star formation and ensures the dwarf fades into a dim, red relic. This missing satellite puzzle forces us to reconsider the very definition of a galaxy. Is it the dark matter halo, or is it the stars that light it up? The evidence increasingly suggests that for every small, shining dwarf galaxy we see, there could be dozens, even hundreds of dark counterparts, galactic phantoms that fulfill the gravitational predictions of our models while remaining completely invisible to our telescopes. Their collective absence from our sky is not a failure of the theory, but a profound lesson in how the universe actively filters light, deciding which structures will shine and which will forever remain in the shadows. Galaxy clusters act as cosmic time capsules, preserving a record of galactic life and death across the eons. In the 1980s, astronomers Harvey Butcher and Butcher-Omeler made a startling discovery while peering back in time at distant clusters. They found that these faraway swarms contained a much higher fraction of blue, star-forming galaxies than similar clusters do in our local, modern universe. This Butcher-Omeler effect reveals a universe in a state of constant metamorphosis, where the vibrant blue spirals of the past have been systematically transformed into the quiet, red ellipticals we see today. The clusters themselves are the engines of this change, their dense environments acting as galactic pressure cookers that accelerate evolution. A spiral galaxy falling into a cluster for the first time faces a gauntlet of hazards. It first encounters the cluster's vast halo of hot plasma, a gaseous medium so searing that it can rip away a galaxy's own cold gas reservoir simply through the force of its passage. This process, called ram pressure stripping, is like driving a car through a torrential downpour where the wind violently tears the water away from the windshield. For the galaxy, this stolen gas is the raw fuel for future stars. Stripped of this material, its star formation is strangled in a relatively short cosmic timespan. At the same time, the galaxy is subjected to relentless gravitational harassment. The combined pull from hundreds of neighboring galaxies and the cluster's immense dark matter halo tugs and distorts the incoming spiral. These rapid, close encounters, known as galaxy harassment, can rip away a galaxy's outer stars and dramatically disrupt its elegant spiral structure, shaking it into a more amorphous, blob-like shape. The galaxy does not explode, it is simply and thoroughly remodeled. Its brilliant blue light, fueled by short-lived massive stars, fades away as star formation ceases. What remains is the cooler, redder glow of its older stellar population. The galaxy has not vanished in a literal sense, but it has effectively disappeared as the distinct, recognizable system it once was. Its light signature changes so fundamentally that it crosses a threshold, becoming something else entirely. This transformation explains why the cores of ancient clusters are dominated by these red and dead galaxies. They are the survivors of a brutal environmental selection, their original forms erased by the collective might of the cluster. Each red galaxy represents a story of a blue spiral that fell into the crowd and had its light systematically altered, a quiet testament to the dynamic and often violent processes that shape the visible universe. The light from the most distant quasars carries a hidden message written in absence. As this ancient radiation journeys for billions of years, it passes through countless clouds of primordial hydrogen, and these clouds leave a distinct fingerprint on the light by absorbing very specific wavelengths. When astronomers first analyzed the spectra of these incredibly remote beacons, they discovered a profound and puzzling gap, a region where the expected light was almost completely missing. This void is known as the Gunn-Peterson Trough, a silent testament to a time when the universe was anything but transparent. The trough appears because neutral hydrogen atoms are exceptionally efficient at absorbing a particular ultraviolet wavelength known as Lyman alpha. In a perfectly clear, modern universe, the light from a quasar would show a continuous spectrum with only a few, sharp absorption lines from intervening hydrogen clouds. But when you look at the light from quasars at extremely high redshifts, you see something completely different, a broad, deep trough where the light has been almost entirely erased. This is not the signature of a few clouds, but of a pervasive, all-encompassing fog. It indicates that at some point in the distant past, the space between galaxies was filled with a thick soup of neutral hydrogen, a medium that acted like a cosmic sponge, soaking up the ultraviolet light from the earliest stars and galaxies. Imagine a dense forest where the canopy is so thick that no direct sunlight reaches the forest floor, only a dim, filtered green glow. For a galaxy shining in that era, its most energetic light was trapped, its story imprisoned by the very medium from which it was born. This absorption feature is a direct probe of the universe's transparency, or lack thereof. The depth and shape of the Gunn-Peterson Trough allow cosmologists to map the timeline of reionization with remarkable precision. They can determine when the fog began to lift, as the first luminous objects, from frantic starburst galaxies to brilliant quasars, started burning bubbles of ionized transparency into the neutral gloom. A complete trough tells us we are looking back to a time before these bubbles fully merged, when the universe was still largely opaque. A shallower trough, or its complete absence, shows we are looking at an era after reionization was complete, when the cosmic pathways had been cleared. This means there is an entire population of the very first galaxies whose light we will never see directly, not because our telescopes are not powerful enough, but because the universe itself absorbed their ultraviolet emissions, systematically hiding them from one of our key methods of observation. Their existence is confirmed only by the shadows they cast, by the very fact that they were ultimately able to burn away the fog that once concealed them. The trough is a ghost in the data, a cosmic silence that speaks volumes about an age of darkness and the first faint lights that fought to be seen. A galaxy breathes. Far from being static islands, these cosmic structures maintain a complex, dynamic circulation of their lifeblood, the gas that forms new stars. This process, known as a galactic fountain, is a cycle of creation and renewal that directly controls a galaxy's brilliance over billions of years. The fountain begins in the galaxy's disk, where the intense radiation and powerful stellar winds from massive stars, along with the shockwaves from supernova explosions, superheat vast volumes of gas. This energized material erupts outward, flowing at tremendous speeds high above the galactic plane into a vast, extended halo. There, the gas begins to cool, condensing into dense clouds that eventually lose their momentum. Pulled back by the galaxy's gravity, these clouds then rain down upon the disk like a cosmic waterfall, returning fresh fuel to the stellar nurseries below. This continuous cycle regulates star formation, preventing the galaxy from either burning through its fuel too quickly or letting it lie fallow. We can see this process in action within our own Milky Way. Observations reveal enormous, arching structures of hot gas, known as the Fermi bubbles, extending thousands of light-years above and below the galactic center, likely the remnants of a past colossal fountain event. In other galaxies like Messier 82, we witness the explosive bipolar outflows driven by a ferocious starburst, a fountain operating at its most extreme intensity. But what happens when this delicate circulatory system fails? If the fountain's outflow is too powerful, the gas might be flung so far that it escapes the galaxy's gravity entirely, lost forever to the intergalactic void. Alternatively, the gas could become trapped in the hot halo, taking too long to cool and fall back, effectively stranding the star-forming fuel in a galactic reservoir that the disk cannot access. Computer simulations show that these interruptions can permanently alter a galaxy's fate. A sustained break in the cycle means no fresh gas returns to the disk. Star formation sputters and then ceases. The galaxy's vibrant blue light, powered by its youngest stars, fades away, leaving only the dimmer, redder glow of its aging stellar population. Over cosmic timescales, this gradual dimming can cause a once brilliant spiral to effectively disappear from the view of distant observers, its light production choked off not by a sudden catastrophe, but by the silent failure of its own internal breathing. The longevity of a galaxy's light appears to depend on the stability of this great cosmic circulation, a rhythm that, once broken, leads to a quiet and permanent fade to black. Our cosmic vision is filtered through an invisible force that permeates the void. Immense magnetic fields stretch between galaxies, weaving through the vast expanses of interstellar space. These are not the simple magnets of a classroom experiment, but colossal, dynamic structures born in the turbulent hearts of stars and stretched to cosmic scales by the expansion of the universe itself. Their influence on light is subtle yet profound, acting like a gentle but persistent lens that can systematically distort our view. When light from a distant galaxy travels for millions of years to reach us, its journey is not through a perfect vacuum. It passes through these magnetized corridors, and the magnetic fields can cause the light waves to oscillate in a specific direction, a phenomenon known as polarization. This is similar to how polarized sunglasses block scattered glare, allowing only aligned light waves to pass through. In the cosmic context, this polarization can subtly change the apparent properties of the light we receive, and in some cases, even redirect it away from our line of sight. For extremely distant and faint galaxies, this magnetic filtering could be the final straw, pushing their already tenuous signal below our detection threshold. The light is not absorbed or destroyed, but its character is altered just enough to make it vanish from our surveys. We have observational evidence for this from studies of the cosmic microwave background, the afterglow of the Big Bang, which shows a faint but measurable polarization imprinted by the universe's primordial magnetic fields. More recently, astronomers mapping the distribution of galaxies have noticed curious, large-scale patterns that are difficult to explain with gravity alone. Some vast regions appear suspiciously smooth, lacking the expected clumpiness of galactic structures. One compelling explanation is that intergalactic magnetic fields are creating a systematic bias, subtly scattering the light from certain populations of galaxies and making those volumes of space appear emptier than they truly are. These magnetic fields could be acting like a cosmic haze, not of dust but of pure force, dimming and redirecting the collective light of countless galaxies and leaving behind the illusion of a void. This means our deepest maps of the universe may carry a hidden distortion, a fingerprint of these immense, invisible magnets that guide the very light we use to see. Our telescopes have always favored the brilliant and the bold. For generations, the census of the cosmos has been skewed by a fundamental limitation known as the surface brightness selection effect. This is not a flaw in our instruments, but a simple fact of observation. Galaxies that concentrate their light into a small, bright area are far easier to spot than those that spread the same amount of starlight thinly across a vast expanse. Imagine trying to see a single high-powered flashlight from a mile away. It is a simple task. Now, imagine trying to see 1,000 faint, widely spaced Christmas lights at the same distance. Their collective glow might be identical, but it would blend into the background and disappear. This is the challenge astronomers face with low surface brightness galaxies. Their total light output might be immense, but because it is so diffuse, it falls below the detection threshold of our surveys, rendering them effectively invisible. This bias has profound implications. It means our map of the universe is not a true representation of reality, but a map of the most obvious landmarks, missing entire continents of faint, ghostly structures. The discovery of ultra-diffuse galaxies in clusters like Coma was a watershed moment. These systems can be as large as the Milky Way, yet they contain so few stars that their light is nearly imperceptible. For decades, they were simply part of the empty background, their faint smudges dismissed as noise or artifacts. Only with meticulous observation and advanced image processing did these phantom giants finally step into the light, revealing a population of galaxies we never knew existed. But the most dramatic correction came from surveys specifically designed to hunt for these faint objects. When astronomers looked at the nearby Virgo cluster with this new sensitivity, they found hundreds of previously unseen low-surface brightness dwarfs. The cluster was not just populated by a few dozen bright galaxies, it was teeming with a hidden populace of faint, diffuse systems that outnumbered their brighter cousins. This discovery forces a complete reassessment of the total light in the universe. If every cluster, every group, every filament of the cosmic web is filled with these dim galaxies, then the amount of stellar light we have been counting is only a fraction of the whole. The universe may be far brighter in its totality than we ever imagined, but the majority of that light is not concentrated in brilliant beacons. It is smeared across the void in a faint, pervasive glow that has been hiding in the background all along. A galaxy's destiny is written in the kinds of stars it births. The initial mass function is a cosmic rulebook for star formation, a statistical prediction of how many heavyweights, middleweights, and featherweights will ignite from a cloud of gas. For decades, astronomers assumed this rulebook was universal, that all galaxies, from the smallest dwarf to the largest spiral, produced the same distribution of stellar masses. But what if the universe is not so uniform? New theoretical models are challenging this long-held belief, suggesting that the initial mass function might be a flexible law, changing from one galactic environment to another. In some quiet, gas-poor galaxies, the process of star formation might be biased, producing a population dominated by small, cool, red stars. These stellar lightweights are the misers of the cosmos, burning their nuclear fuel with incredible frugality and living for trillions of years, but they emit only a faint, reddish glow. A galaxy filled with such stars would be a dim place indeed, its total light output a mere fraction of a similar-sized galaxy that formed brilliant, short-lived blue giants. This concept, known as the integrated galactic initial mass function, could solve a persistent discrepancy in our cosmic accounting. Our best models of cosmic structure predict a certain amount of light from the vast population of small, faint galaxies that should fill the universe. Yet when we add up all the light we actually see, the numbers fall short. There is a gap, a deficit of observed starlight. One compelling explanation is that a vast number of these faint systems are not just small, but are inherently dim because they formed the wrong kinds of stars from the very beginning. They are not missing, they are simply operating on a different set of rules, producing a faint, red stellar population that slips beneath the detection limits of our most powerful telescopes. Imagine two factories with the same amount of raw material. One produces a few brilliant, high-wattage searchlights. The other produces millions of tiny, low-power LED bulbs. The total energy consumption might be similar, but the visible brilliance from a distance is worlds apart. This is the subtle but powerful effect of a varying initial mass function. It means that when we look into a seemingly dark void, we might not be looking at an empty volume of space, but at a region teeming with galaxies that chose to build with faint, red embers instead of brilliant blue flames. Their stories are not lost, they are simply written in a light too dim for our current eyes to read. Our cosmic address might be far more unusual than we ever suspected. Evidence is mounting that our Milky Way galaxy resides inside a colossal bubble of relative emptiness, a region known as the KBC Void. This isn't a perfect vacuum, of course, but a vast underdensity spanning over 2 billion light-years, where the concentration of galaxies and galaxy clusters is significantly lower than the cosmic average. We are living in a local cosmic desert, a fact that profoundly skews our perspective on the entire universe. When we peer out from our relatively sparse neighborhood, we are looking from the inside of a void toward the denser walls of the cosmic web. This unique viewpoint directly impacts how we measure fundamental properties of the cosmos, including the rate of its expansion and the true average density of galactic light. The Hubble constant, the number that describes how fast the universe is expanding, has been a source of intense debate. One method uses the cosmic microwave background, the afterglow of the Big Bang, while another uses nearby supernova as distance markers. These two methods persistently yield different results, a discrepancy known as the Hubble tension. Living inside a giant void could be the key to resolving this puzzle. From our underdense local position, the gravitational pull of surrounding matter is weaker. This allows space around us to expand faster than in the crowded regions outside the void. Our local measurements of expansion would therefore be higher, potentially explaining why the supernova method gives a different answer than the method that probes the entire universe's average. This same principle applies to the mystery of lost light. If we are situated in a sparse region, our census of nearby galaxies will naturally be lower. What we might interpret as a universal phenomenon of galactic disappearance could, in part, be a simple consequence of our unlucky location. We are like astronomers living in a secluded valley trying to map a continent. From our limited vantage point, we might conclude that mountains are rare when in reality we are simply standing in one of the few flat places. The debate around the KBC Void is far from settled, with some cosmologists arguing that such a large underdensity is statistically unlikely in our standard model of the universe. Yet its potential existence forces a humbling realization. Our map of cosmic light is not an objective chart, it is a view from a single, and perhaps unrepresentative, window. The galaxies we see as missing might be thriving just beyond the walls of our local void, their collective glow hidden by the simple, sobering fact of our own cosmic isolation. An invisible ocean washes through the cosmos, a ceaseless tide of nearly massless particles born in the fires of the Big Bang. These cosmic neutrinos outnumber atoms by billions to one, flowing through you and everything else in the universe as if it were not even there. For the longest time, we considered them mere cosmic spectators, ghostly passengers with no real influence on the grand structures of space. But we are now learning that this neutrino background radiation may be a quiet architect in the story of galactic disappearance. Their collective gravity, though unimaginably faint from a single particle, becomes a tangible force when summed across trillions of light years. This subtle gravitational pull can act as a form of cosmic friction, gently tugging on the vast reservoirs of dark matter that cradle galaxies. Over billions of years, this persistent influence could subtly alter how dark matter halos grow and merge, potentially disrupting the very gravitational anchors that hold galaxies together. It is a slow, almost imperceptible pressure, but across the lifespan of the universe, it could be enough to nudge a galaxy toward instability, making it more susceptible to being torn apart by the more violent forces we have already discussed. Theoretical models suggest an even more direct role. In the earliest moments of galaxy formation, the pressure from this dense neutrino background could have influenced how and where the first clouds of gas collapsed. By providing a slight, uniform push, neutrinos may have filtered out the faintest, most tenuous protogalaxies, preventing them from ever igniting their first stars. This would mean a portion of the universe's missing small galaxies were not stripped or quenched, but were stillborn, their light never kindled because of a gentle pressure from a sea of ghosts. The quest to confirm this shadowy influence is driving the design of next-generation detectors. These are not optical telescopes, but immense, hypersensitive laboratories buried deep underground to shield them from other cosmic interference. Their goal is to map the precise energy and flow of the cosmic neutrino background. By understanding its properties, we can run more accurate simulations of the universe's evolution, seeing if the inclusion of this neutrino gravity solves the lingering discrepancies in our galactic maps. If these models are correct, we may find that a significant portion of the universe's lost light is not lost at all, but was never allowed to shine in the first place, its potential erased by the gentle, relentless push of the universe's most abundant and elusive particles. The cosmic story is still being written, and its final chapters are darker than we ever imagined. Billions of years from now, the universe will be a far more isolated and dimmer place, a direct consequence of the same expansion that shapes it today. As space continues to stretch at an accelerating rate, the very architecture that allows us to see distant galaxies will be systematically dismantled. The cosmic web, that grand tapestry of filaments and clusters, will begin to fray at the edges and then tear apart at its core. Galaxy clusters themselves, those immense gravitational islands, will become the final fortresses of light in an ever-expanding sea of darkness. Our own local group, a collection including the Milky Way and Andromeda galaxies, will eventually merge into a single, giant elliptical galaxy. For any astronomers living within that future system, the view from their window will be profoundly lonely. Every other galaxy group will have been swept beyond an unreachable horizon, their light stretched into undetectability by the relentless expansion of space itself. The universe outside their galactic island will appear utterly black and empty, a void from which no new light can ever reach them. This is not a sudden event, but a slow, inexorable fading. The process is driven by extreme cosmological redshift. As the space between these isolated galaxy clusters expands faster and faster, the light trying to cross that gap is stretched to an extreme degree. The visible light from stars is shifted far beyond the red end of the spectrum, through the infrared, and into the realm of radio waves with wavelengths so long they become impossible to distinguish from the background whisper of the cosmos. The galaxy does not blink out. Its light is simply transformed into a form that is fundamentally undetectable, a ghost signal lost in the static of the universe. What does this mean for the ultimate fate of cosmic light? Current models suggest that in about 100 billion years, only the combined stars of that single, merged local galaxy will be visible. All other galactic light will have redshifted into oblivion. The evidence for the Big Bang, the cosmic microwave background radiation, will have faded away entirely, its wavelengths stretched to such an extent that they effectively disappear. For those future beings, the cosmos will consist of their one galaxy adrift in an infinite, static blackness. They would have no way of knowing that a vast, dynamic universe of galaxies ever existed. All the evidence for expansion, for a violent beginning, and for a cosmic web of structures would be permanently erased from their view. This is the ultimate disappearance, a future where the universe actively hides its own history and scale, leaving its final inhabitants in a solitary galaxy, staring out at a perfect and eternal night, unaware of the brilliant cosmic dawn that preceded their lonely era. Every signal the cosmos sends us is a single thread in a much larger tapestry. For centuries, we have relied almost entirely on just one of these threads, light, to read the story of the universe. But now, a new era of observation is dawning, one that listens to the universe as intently as it watches. This is multi-messenger astronomy, a field that combines the traditional study of light with the detection of gravitational waves, neutrinos, and cosmic rays. By weaving these different messengers together, we are building a far more complete picture of reality, one that is finally allowing us to detect galaxies that have been completely invisible to our telescopes. Light can be blocked, stretched, or absorbed, but gravitational waves are ripples in the very fabric of space-time itself, produced by the most violent cosmic events. When two black holes or neutron stars spiral together and collide, they shake the universe, sending out waves that travel unimpeded through dust, gas, and even entire galaxies. In 2017, the LIGO and Virgo observatories detected such a wave from a pair of merging neutron stars. Almost simultaneously, telescopes across the globe saw a brilliant flash of light, a gamma-ray burst from the same patch of sky. This single event, observed through both gravity and light, confirmed a long-held theory and demonstrated the immense power of this combined approach. But the true promise for finding lost galaxies lies in the events we cannot see. Imagine a merger of two supermassive black holes at the heart of a galaxy, shrouded in an impossibly thick cocoon of dust. No light, from radio waves to gamma rays, could ever escape to tell us the story. Yet the titanic collision would unleash a storm of gravitational waves, a clear signal announcing the galaxy's presence and its most dramatic secret. Our detection of neutrinos offers another path into the darkness. These ghostly particles, born in the hearts of stars and cataclysmic explosions, travel in near-perfect straight lines from their source. In 2018, an observatory buried deep in the Antarctic ice detected a single, high-energy neutrino. Astronomers traced its path back to a distant blazar, a galaxy centered on a gluttonous supermassive black hole spewing a jet of radiation directly at Earth. This was a landmark proof that we can use particles, not just photons, to pinpoint energetic galaxies across the cosmos. This multidisciplinary approach is fundamentally changing the rules of our cosmic senses. A galaxy is no longer defined solely by the light it emits, but by the total sum of its observable phenomena, its gravity, its particles, and its radiation. A dark galaxy, a massive structure with no stars, might reveal itself only by subtly bending the light of a more distant object through gravitational lensing. An otherwise quiet galaxy could be flagged by a torrent of neutrinos from a single, colossal supernova hidden within its core. We are learning that the universe is shouting at us in many different languages. For too long, we have been listening to only one. By finally tuning into the full spectrum of cosmic messengers, we are pulling back the final veil, discovering that what we once called empty space is in fact a vibrant chorus of unseen galaxies, each telling its story in its own unique voice. These vanishings force a confrontation with the very nature of knowledge itself. If we can only observe a fraction of the cosmos, how can we ever claim to understand its true architecture? Our maps are not just incomplete, they are fundamentally skewed, filled with phantom absences and ghostly echoes that challenge the idea of a knowable universe. This is not merely a technical problem for astronomers, it is a deep philosophical puzzle about the limits of observation and the reality we can perceive. The lost light represents a permanent horizon for human knowledge, a boundary beyond which we may never see. This concept echoes a principle from quantum mechanics, where the act of observation itself alters the system being observed. On a cosmic scale, our gaze is passive, yet the universe still presents a different face depending on the tools we use and the questions we ask. We are not just mapping the cosmos, we are in a constant dialogue with it, and its replies are filtered through the immense distortions of space, time, and matter. What does it mean for our place in this vastness if entire chapters of cosmic history are written in a light we cannot read? Some philosophers of science argue that this forces a kind of cosmic humility. We must accept that a complete and perfect model of the universe might be forever beyond our grasp, not because of a lack of intelligence, but because of the inherent physical limitations placed upon a species living within the very system it tries to comprehend. We are like sailors trying to chart the entire ocean from a single, moving boat, aware that distant storms and hidden currents remain forever outside our view. The phenomenon of disappearing galaxies transforms our quest from a simple hunt for facts into a more profound exploration of meaning. It suggests that the universe is not a static museum exhibit laid out for our inspection, but a dynamic, evolving entity that actively conceals as much as it reveals. Each galaxy that fades from view is a reminder that the cosmos holds secrets it may never relinquish, and that the greatest discovery might be the acceptance of our own permanent, and perhaps necessary, ignorance. The hunt for vanishing galaxies has now expanded to include millions of assistants from all over the planet. Modern astronomy has opened its digital doors, inviting the public to become active participants in the search for cosmic ghosts. This global collaboration, known as citizen science, leverages a powerful resource that even the most advanced computers lack: the human brain's innate ability to recognize patterns and spot anomalies. When you are faced with a million images of galaxies, an algorithm can sort them by size and brightness, but it takes a human eye to notice the subtle strangeness, the faint tidal stream, or the odd asymmetry that signals a galaxy in the midst of a dramatic transformation. Online platforms like Galaxy Zoo and Zooniverse have become virtual control rooms for this collective endeavor. Volunteers from all walks of life log on to classify images from the world's great telescopes, sorting spiral arms from elliptical blurs. In the process, they sometimes stumble upon something truly bizarre: a galaxy that looks like it is being stretched apart, or a system with a mysterious dark lane where stars should be. These are the clues that point to the very processes of disappearance we have been exploring. The collective power of this distributed human network is astonishing. It was citizen scientists who first identified a whole new class of galaxies they called green peas, small, compact, and intensely star-forming systems that had been overlooked in automated scans. They have helped catalog countless gravitational lenses, the very tools we use to detect invisible dark matter and dark galaxies, and they are perfectly positioned to flag galaxies that look different from one survey to the next, potential candidates for real-time disappearance. This human-augmented research complements artificial intelligence, creating a powerful partnership. An algorithm can process data at lightning speed, but it needs to be trained on what to look for. The intuitive classifications made by thousands of volunteers provide that essential training set, teaching machines what a galaxy on the edge of dissolution truly looks like. Every click from a volunteer is a single data point, but together they form a vast net cast into the cosmic ocean, capable of catching the faint, fleeting signals of change that would otherwise slip through. This collaborative spirit redefines the search for lost light, transforming it from a solitary scientific pursuit into a shared human adventure, where anyone with curiosity and an internet connection can help piece together the universe's greatest disappearing act. Our ability to see the cosmos depends entirely on the tools we build, and those tools are shaped by the economic realities of our world. The grand quest to understand vanishing galaxies is not just a scientific endeavor, it is a story of funding, politics, and technological leaps. The specific disappearance phenomena we can even attempt to study are dictated by the capabilities of our current observatories, creating a profound and uneven map of cosmic knowledge. A nation with the resources to launch a space telescope sensitive to infrared light will excel at finding galaxies obscured by dust, while a country relying on ground-based optical telescopes might only document the slow dimming of aging stellar populations. This technological divide means our collective understanding of the universe is inherently patchy, filled with blind spots that have nothing to do with the cosmos itself and everything to do with our own earthly limitations. For decades, our cosmic census was skewed toward the bright and the blue, simply because our instruments were optimized to see them. The countless faint, red, and diffuse galaxies slipped through the cracks, not because they were not there, but because we lacked the financial will and engineering prowess to detect them. The priorities of funding agencies create a powerful filter. A multi-billion-dollar mission to study the epoch of reionization will unlock secrets about the universe's earliest vanishing act, while leaving other mysteries like the true population of dark galaxies waiting in the wings for a future budget cycle. This means the history of astronomy is not a smooth, continuous revelation, but a series of dramatic jumps forward followed by long plateaus, each leap powered by a new technological breakthrough. The Hubble Space Telescope revolutionized our view by rising above the distorting effects of Earth's atmosphere, but it was still blind to the infrared universe. That frontier had to wait for the James Webb Space Telescope, a project that required decades of international investment and political negotiation. What we know about galactic disappearance is therefore a direct reflection of the technologies we have chosen to fund and build. This uneven progress explains why some cosmic vanishings, like galactic mergers, are well documented, while others, like the subtle effects of the cosmic neutrino background, remain in the realm of theoretical speculation. Our vision of the cosmos is a direct projection of our own technological and economic ambitions. The next great observatory, whether it listens for gravitational waves or sees in untested wavelengths, will not just answer our current questions, it will inevitably reveal new classes of cosmic ghosts we do not yet have the language to describe. Every time we build a better window to the universe, we are also building a new set of mysteries, ensuring that the final frontier of knowledge forever recedes before us. The way we share these cosmic secrets matters just as much as their discovery. When astronomers announce that a galaxy has vanished, the public is captivated, but the complex physics behind the event can create a wall of confusion. Bridging that gap is essential, not just for funding, but for fostering a society that feels connected to the universe it inhabits. The key lies in translation, transforming dense astrophysical jargon into a language of wonder and narrative. Instead of presenting dark matter tidal stripping as an abstract force, we can frame it as a cosmic detective story. Imagine presenting the evidence, the faint streams of stars, and asking the audience to become sleuths, piecing together the identity of the invisible culprit. This approach does not dumb down the science, it humanizes it. By framing galactic disappearance as an ongoing mystery, we invite everyone to participate in the search. Planetarium shows, popular science books, and online videos that depict the universe as a dynamic, sometimes violent, and always changing arena capture the imagination in a way static facts never could. They reveal that science is not a list of answers in a textbook, but a living, breathing process of inquiry. This perspective is incredibly powerful for inspiring the next generation. A child who learns that galaxies can collide, fade, or be hidden might just see themselves as the future astronomer who finds out why. That spark of curiosity is the foundation upon which future missions are built and great discoveries are made. For the general public, understanding these concepts reshapes their entire cosmic perspective. It moves the universe from a backdrop of pretty pictures to a character in an epic story, one with a past, a present, and a future that is still being written. When people grasp that the sky is not permanent, that the light we see is a fragile message from a changing cosmos, it instills a profound sense of connection and humility. Effective communication turns distant, academic phenomena into shared human experiences, ensuring that the quest to understand our disappearing universe remains a collective and enduring adventure. Our journey ends where it began, in the quiet mystery of the missing light. The cosmos is not a static museum exhibit for our observation, but a living, breathing entity in a state of perpetual transformation. Galaxies do not simply vanish, they are unmade by the universe's own rules, their light stolen by dark matter's pull, stretched into invisibility by expanding space, or quietly absorbed by cosmic dust. We have chased these ghosts through the lenses of our most powerful telescopes, only to find that our vision is filtered through both physical barriers and the inherent limits of our own technology. Each mystery we solve, from the quenching of a galaxy's inner fire to the phantom pull of a dark galaxy's gravity, peels back one layer of the cosmic veil, only to reveal another waiting beneath it. This endless cycle of discovery and new questions is the very engine of our curiosity. The search for lost light is far more than a technical puzzle. It is a profound lesson in cosmic humility. It reminds us that our map of reality will always be a work in progress, a sketch drawn from a single, fleeting perspective in an unimaginably vast and ancient cosmos. Yet this same incompleteness is what drives us forward, compelling us to build better tools and ask deeper questions, forever reaching for the next glimmer of understanding in the